Hey, welcome back everyone. So my name is Zach Vines, and what we're going to look at today is very similar to two previous videos I made, which I'm going to go ahead and say I'll link those in the description for you to see before you watch this video. But essentially we're just talking about confidence intervals, how to solve for them, but specifically how to solve for them in Excel. So I'm not going to harp too much on the exact formula because it's going to be the exact same formula for what I talked about in the previous two videos in the description. But there are certain variables within these formulas that if you're not forced, but if you're supposed to use Excel for your class, or if you just want to be more precise with your calculation, there's certain values you can solve for in Excel, and we're going to go through how to do that. And so essentially what we're talking about is just the overall confidence interval formula where we have the point estimate, where the point estimate is either going to be X bar, which is just your sample mean, and you use that if it's a mean-based problem, or it's going to be known as F, assuming that that's the variable used for your class. I've seen sometimes the sample proportion is known as P and other variables, but I know that as being F. If it's a proportion-based problem, that's going to be your point estimate. So just plug that in accordingly. And then whenever we're solving for a Z or T, we're going to decide whether or not we do a Z value or a T value based on a few things. So T or Z, either way, you're going to have to make sure it's a positive number. But just to kind of talk about T first, if you do not know the population standard deviation for the problem you're given, you have to use the T value, okay? So in that case, when you're solving for it in Excel, you're going to say equals T dot INV, and the fields that it asks you to fill in for that are probability and degrees of freedom. Simply, your probability is going to be 1 minus your confidence level. So in problems, they'll give you things like 90%, 95%, 99% confidence level. So for instance, if it was 90%, I would do 1 minus 0.9, take that number and divide it by 2, and that's the value I'm going to put in for the probability. Then for degrees of freedom, it's just simply n minus 1, where n is the number of things that we're sampling for that particular sample. So basically the number in the sample minus 1 is the field that you put in right there. So there's a lot more to write as far as the Z value and the standard error goes, just didn't have enough room. So now we're going to talk about the Z value and when you use that. Okay, so now we're talking about whenever we use a Z value instead of a T value. And so before with the T, we would do it if we did not know the population standard deviation, and if we would use a Z value in these situations. Where we do know the population standard deviation, and one other time, and it's a really big note to make, if it's a proportion-based problem, you just go straight to the Z value right there. So if you have, a part out of a whole, we're not wondering about a mean or an average, but rather a percent of falling into some criteria out of a total. In that case, don't worry about the population standard deviation, just jump straight into this Z value formula right here, and you should be good to go. And so the Excel function we use for that is equals norm.s.inv, and we have to fill in the probability. That's the only field you have to worry about for that Excel function. And the probability for it is just like the probability you had to solve for in the other function that we just went over, where it's 1 minus the confidence level, so either the 90, 95, or 99% are the standard confidence levels you'll see. Take that and divide it by 2. And again, the answer that it spits out, it's almost always going to be a negative number, or at least in many cases it is. Make sure that's a positive number when it comes out. So there's a couple of ways you could do that. The way I like to do it, and this might be right or wrong compared to some people, but if you just simply say equals negative and then cell reference the answer you get for norm.s.inv, it just turns it into a positive number. You could even say equals, do the absolute value function and highlight the answer you get. There's a few different ways, but you just want to make sure the answer that's put out for this is a positive number. So the only other thing to go over before some examples is the standard error. So let's get into that right now. Okay, so the last part of the formula is just the standard error, which keep in mind for both of these formulas right here, what you're solving for is still the standard error. So even though the exact formulas for them are different between which situation we fall under, if you can keep in mind this overall broad formula and just kind of drill down which situation you fall into from there, it'll be a lot clearer. In just a moment after this, we're going to go over two different examples to kind of show you how important it is to lock this in and drill it down using the steps that we just laid out, and you'll see how it works. But just as an overview, for mean-based problems where we have an average value, it's the standard error is simply going to be the standard deviation, just whatever S is. You might see it as a different symbol as well, but many of us see it as S, just the standard deviation divided by the square root of n, which again is just the number in the sample, however many things we're sampling in that situation. And for a proportion-based problem, it's a bit of a funkier calculation, but it's a big square root. Take your sample proportion, so whatever the part you're interested in out of the whole for that particular sample, that proportion, take that, multiply it by 1 minus that proportion, divide by n, which again is the number in the sample, big square root, and that'll give you the standard error. So let's go ahead and run through two quick problems, and I think it'll make everything a lot clearer. Okay, so for this particular problem, we're given this information over here. So this is the example I like to use anytime I'm tutoring someone, so I'm sorry if I've helped you out before and this is just redundant at this point. But at this point, we're trying to find out what is the average height of students at my university. Okay, so I go and I'm wondering that situation. So I go and I collect a sample of 200 students, and I find out that the mean height of those 200 students is 67 inches, okay? So at this point, I'm wanting to create a 95% confidence interval based on the information. So just make sure you have the formulas written down from what we just went over, because I'm really just going to start with that and drill it down based on everything we just talked about. So if you have that, you should be able to do this no problem. So here's what's going on. The overall formula is our point estimate plus or minus our z or t times our standard error. Okay, well the point estimate, we said that was either going to be x bar if it was a mean-based problem or f if it was a proportion-based problem. Well, in this situation, we're talking about a sample of 200 students and what their average height was. Since I'm wondering about an average height or a mean value, the point estimate I put in is going to be x bar. So I'm just laying the groundwork right here, and then we'll take care of it from that point on. So x bar is going to be my point estimate. Now, am I dealing with a z or a t in this situation? Well, we know that we'll have a z value if one of two things happens. It's either a proportion-based problem, which it's not the case here. We just established it's a mean-based problem. Or if you do know the population standard deviation, you're going to use z. Well, here, based on the information we have, they don't say anything about a population standard deviation. So absent any other information, we'll have to assume we're going to do a t value right here. So we're going to use the equals t.inv formula and plug into it in just a moment. Finally, whenever we're dealing with a mean-based problem, we know that the standard error is simply s, the standard deviation, divided by the square root of n, okay? So in this situation, so we should also know that the standard deviation is 2, so I forgot to write that down. So I'll go ahead and say s equals 2 right here. But apart from that, we're just going to fill in the formula. So our x bar is going to be 67 because they say that the mean height in our sample was 67 inches. And x bar stands for the mean of your sample, so we just plug in 67. So we're going to do plus and minus, and that'll give us the lower bound and the upper bound we'll get to in just a moment, equals t.inv that we just discussed a moment ago. We're going to fill in the probability right here. The final answer you get for that is going to be 0.025, and here's why. Before we said that the way you solve for that probability is 1 minus the confidence level, take that value and divide it by 2. In this situation, our confidence level is 95%. So I took 1 minus 0.95, I got 0.05 from doing that. Then I divided it by 2, gave me 0.025. So that's how you plug it in right there. Just take 1 minus your confidence level, that value, divide it by 2, plug it in for the probability in this Excel function. Finally, with the degrees of freedom, we just established that the sample was 200 students. We know that our degrees of freedom is n minus 1, so 200 minus 1, 199. Finally, when we're dealing with standard error, that's just s divided by square root of n. So I had to fill in, I forgot to put that information there, but we are given the fact that our standard deviation for the sample is 2. So I'm simply going to put in 2 divided by the square root of 200, the number in the sample. So from there, I'm just going to continue solving for it. 67 is the same 67 from before. Now this equals t.inv, when you plug this in, what it spits out in Excel is likely going to be a negative value. It's probably going to tell you negative 1.97. If that's not the case, don't worry about it. You have the positive number. If that is the case, you need to make sure that this 1.97 is a positive number when you're filling it into your confidence interval formula. So again, you can say equals, I think it's ABS is the absolute value function. Either way, you do the absolute value function on the output you get, and it'll give it to you in positive terms, or you can just say equals negative, then cell reference the value you get when you do this function, and it'll just turn it positive. You want this to be a positive number. And then finally, when you do 2 divided by square root of 200, you get 0.14. So at this point, all we have to do is multiply these two things together. That value is going to be subtracted from 67 to give us our lower limit. That value is going to be added to 67 to give us our upper limit, and that's our confidence interval. So one thing I want to point out that I have mentioned in the previous videos is that this z or t value times your standard error gives you something known as the margin of error. So you may be specifically asked, what is the margin of error for this problem? It's simply going to be whatever you got for z or t, take that, multiply it by your 0.14, and that's how you get your margin of error. And this is also the number that's going to be subtracted from 67 to give you your lower confidence limit. So I'm going to do 67 minus my margin of error, gives me my lower confidence limit. My upper confidence limit will be 67 plus that, hence the plus and minus, plus the 0.2789 gives us 67.28. So our final answer, our full confidence interval, is 66.72, 67.28. And the way you can interpret that is that we can say with 95% confidence that the mean height of UAB students falls somewhere in between 66.72 and 67.28. So the students at my university, it's going to fall somewhere in between that. So that takes care of a mean-based problem. So let's move into one more to kind of wrap things up. All right, so the very last example we have here is very similar to what we just did, and I intentionally did that because I wanted to show the difference between a mean-based problem and a proportion-based problem. So in this situation, we're still wondering about the height of students at my university, but in this situation, we're wondering specifically what percent of students are over 65 inches tall at my university. So instead of wondering about a particular number, I'm just interested in some proportion of students above a certain height. So in this situation, we have a sample of 150 students, and we know that 90 of them out of the sample that we took are over 65 inches tall, which is what we're interested in. So now we just have to construct a 99% confidence interval. So we're going to go through the same process we did before, start with what we have at kind of at the broad level, drill down from there, and get the answer. So again, the formula is your point estimate plus or minus z or t times standard error. That's how you solve for a confidence interval. The point estimate is either x bar or f. X bar if you're dealing with a mean-based problem, or F if you're dealing with a proportion-based problem, which clearly we're dealing with right here. If we're wondering about a percent of students who are over a certain height at my university, not the exact height of them, like the average height, we're wondering about a part out of a whole or a proportion. So we know it's going to be F right there, the sample proportion for the point estimate. Now the Z or T, we said before that, okay, if, whether or not you know or don't know the population standard deviation factors into that, but we also said that if we're given a proportion-based problem, we can just jump straight to the fact that this is a z-based problem, meaning that we would have to use norm.s.inv, not the other function that we talked about before. So just if it's proportion, use the norm.s.inv. And then finally with the standard error, whenever we're dealing with a proportion-based problem, still solve for standard error, but it's a different formula. Big square root the sample proportion times 1 minus the sample proportion divided by n, square root all of that. So to plug into that, our F is going to be 90 divided by 150 because what we're interested in are students who are over 65 inches tall. Well, in our sample, 90 of them were over 65 inches tall. So if that's the criteria we're interested in is the people who are over that certain height, the part we're interested in out of the whole, which is the full 150 students we sampled, gives us our sample proportion, which I say right there is 0.6. So that's going to be our point estimate, plus and minus norm.s.inv. And again, the only field they ask for right here is your probability. So the way I got this 0.005 is just like we talked about before, where we have, in this case, it's 1 minus your confidence level. Take that value, divide it by 2. Here, 1 minus our confidence level, the 1 minus 0.99 gives us 0.01, and 0.01 divided by 2 is 0.005. So plug that in the Excel function, and it should spit you out a number that should be good to go. And then finally, when we're dealing with the standard error, square root of f that we just identified to be 0.6 times 1 minus f, 1 minus 0.6 is 0.4. All that divided by n, which is your number in the sample, square root all of that. So now to solve for each of those, the 0.6 we just identified was f, plus and minus what you get when you plug in norm.s.inv at 0.005 is 2.58. Again, just make sure that's a positive number when it's spit out. It might give you a negative number. Turn it positive through the ways that we talked about before. So it's 2.58. Multiply that by the standard error. When you calculate this out, it gives you 0.04. These two, when you multiply them together, is known as your margin of error. That's going to end up being 0.103, and this is the number that you're going to subtract from 0.6 to get your lower limit, add to 0.6 to get your upper limit. So you see right here, our lower confidence limit is going to be 0.6 minus the margin of error, gives us 0.497. The upper confidence limit is 0.6 plus that margin of error, gives us 0.703. So our overall answer that we have, the entire confidence interval, is 0.497, comma, 0.703. So I hope that helps out. Again, it's very important for you to kind of get the overall idea of what a confidence interval is. This video isn't intended to be all-inclusive for every confidence interval situation. The overview video I provided and the example video I provided whenever we're not dealing with Excel pinpoints that, but really the only difference between those is handling this z or t value right here, because we have to use an Excel function to find that number instead of actually just relying on, oh, 90% tends to be this, and just plugging in the rounded values. When you're using Excel, it's going to give you every decimal point involved with that value. So it's going to be a more precise measurement. It's going to make sure that if you have a rounding error, possibly, and you have to round to a certain number of decimal points when you're plugging in an answer to your tests or your quizzes or whatever the case may be, then it's going to take care of that rounding error for you. So I hope that helped out. Watch the previous videos if you're having any more trouble, and thank you for watching.